Okay, now we're going to put everything together here. We're going to put together the inductor, okay? So the L is for inductor, and we know that the inductor can store energy in the form of a magnetic field. And that's why it produces that back EMF. It takes time for that magnetic field to build up. And we're going to also combine it with a capacitor, which is going to store energy in the form of an electric field. Now, this is really interesting in terms of how we store energy, and has a really nice analogy with the simple harmonic oscillator, because in the simple harmonic oscillator, we have the mechanical system. We trade potential energy in terms of the spring energy with kinetic energy, which is basically the energy of motion. And it'll keep oscillating back and forth between this trade-off of kinetic and potential energy, causing the simple harmonic oscillator to oscillate. We will see the same exact thing going on with this LC circuit, where the inductor is going to trade energy with the capacitor, and the capacitor likewise will give its energy back to the inductor as one complete oscillation takes place. So again, it's this trade-off between one type of energy and another type of energy, magnetic and electric energy, that keeps the system oscillating. And what's also interesting, just like the harmonic oscillator has a resonant frequency, these LC circuits also have resonant frequencies. So keep that in mind as we go through the LC circuit. So again, what is an LC circuit? Well, notice that we've left off the resistance. We're not going to, talk about resistance just yet, because that's going to be a slightly more complicated circuit. But basically here, all we have is an inductor in series with a capacitor. In fact, we're going to even leave off a source of EMF and sort of wave our hands and say, magically, we're going to get a moving current and we're going to have energy in there. In real world examples, an LC circuit might be an oscillating circuit, which is used in an old radio. And there the energy is introduced from an antenna, which is actually connected to the inductor. Okay, so again, our LC circuit, just to remind ourselves, has an inductor, basically our electromagnet, if you will, some type of solenoid. It can be a solenoid, a toroid, or something that is going to be able to produce a magnetic field. We also have our capacitor, okay? And our capacitor is where we're going to store charge. Now, the big thing again is this oscillation, which goes back and forth, where energy is swapped between these two objects. Again, just to remind you, our electric field stores energy in the capacitor, where a magnetic field will store energy in the inductor. And here, oh, I thought this was animated. Okay. Unfortunately, this particular one is not animated. But again, here we can sort of follow exactly where the energy is going. Okay, now let's say I have a charged capacitor. So I've got tons of positive charge over here, and I've got tons of negative charge over here. Okay, so completely charged it up. Now, what naturally is going to happen is when I allow this capacitor to discharge, is the positive charge is going to want to flow away from the positive plate, and it's going to want to flow to the negative plate. As it does that, that is going to reduce the amount of charge. So essentially, as the capacitor discharges, it's giving up its energy. The current begins to flow to the inductor, Well, what does that do? Well, as a current flows through the inductor, that produces a magnetic field. So the energy that the capacitor had now becomes the magnetic field, or becomes stored in the inductor as a magnetic field as the current begins to flow more and more. Well, eventually, enough of the current flows so that my capacitor now has the opposite charge on the lower plate and the opposite charge on the upper plate. And this field's going to get stronger and stronger while the magnetic field begins to give up its energy back to the capacitor. And as you might have guessed, the whole process reverses itself and starts over again. And there's the oscillation that takes place. So initially, if we build up initially, if we build up charge on the capacitor, we allow the capacitor to discharge, that charge becomes flowing current. The current produces a magnetic field. The magnetic field, as the current flows, okay, is going to produce an EMF. This is going to cause the charge to then build up on the capacitor again, and the process just keeps repeating itself over and over again. Okay, so in many ways, this LC circuit can be thought of similarly to the simple harmonic oscillator, which is nothing more than a mass on a pendulum. Okay, now technically, there are three types of energy here. There's the potential energy due to the spring, there's the potential energy due to gravity, and there's the kinetic energy due to movement. All right. So in the LC circuit, we're only dealing with two types of energy: electric field energy and magnetic field energy. But if we forget for a second the potential energy associated with the spring, and just think about potential energy in terms of gravity, the potential energy is greatest when the spring is all the way at the top. And the kinetic energy is greatest when the spring is right in the middle. So we can think about this as, and the potential energy becomes great again on the bottom, as the current will flow from the capacitor through the inductor to produce the magnetic field. So, you know, we have the movement of charge that's almost similar to the kinetic energy of the pendulum. And then it will move to the other plate and reverse the polarity of the capacitor. So again, we build up potential energy. Then that charge goes back the other way and builds up potential energy again. So as we watch this oscillation back and forth, it's very much like the simple harmonic oscillator. And in fact, just like the motion of the simple harmonic oscillator can be described in terms of sines and cosines, the current and the voltage here can also be described in terms of sines and cosines. Instead of a spring and a mass moving here, okay, you have current, which is oscillating back and forth and causing charge to build and discharge. So if we look at the equation that describes the simple harmonic oscillator, and I apologize to those of you who are calculus adverse, we can use, I don't know why the tool didn't change right there. We can use this equation right here, and we know the solutions to this equation. This is actually a branch of mathematics called differential equations. This is an ordinary differential equation. but we don't need to go through all the particulars here, but we can show that the solution here for the position of a simple harmonic oscillator is equal to the amplitude times cosine omega t. Omega is the angular frequency, where omega is equal to the square root of k over m. And again, this simple harmonic oscillator, the mass, is going to move up and down, and its velocity, which is the first derivative position as a function of time, is going to go by sine. Okay. Now again, we think about the LC circuit where we have charge on the capacitor. In this case, for the LC circuit, we have charge which is sort of analogous to X, or the position. Okay. And current is analogous to the velocity of the mass, because that's the movement of charge. If Q is charge, dq dt is current. So there are really the similarities in the LC circuit. Now, let's go back to Kirchhoff's rules. First of all, Kirchhoff's rule says that whatever the current is through the inductor, that's going to also be the current at the location of the capacitor. It's the junction rule. Well, there are no junctions here, so the current's just going to be constant. But we can also see that the voltage across the inductor plus the voltage across the capacitor has to be equal to 0, because we make one full loop all the way across the circuit. Kirchhoff's loop rule says that the change in voltage must be 0 across any closed path. Okay, so let's think about what each of these voltages are. Earlier on, we defined that the EMF due to an inductor was equal to negative L, okay, di dt, okay? So we are going to use that expression right here and say L di dt. I'm using lowercase I here because I is going to be this function that's going to change with time. And I'll use capital I whenever I am talking about, the amplitude of the current. Okay, so the voltage across the inductor goes by this. I, we know, is dq dt. So we can now replace I with dq dt, and it becomes a second derivative of q as a function of time. So that is my first term, right? This right here is this right here. Okay, so I'm going to do the same thing for the capacitor. Okay, here's my capacitor. We know for a capacitor that the capacitance is equal to the amount of charge Q divided by the voltage. So I can rewrite that to say that the voltage is equal to the current divided by, the charge divided by the capacitance. So now that gets plugged in right there. And I get from that a differential equation, which is almost identical in form to our simple harmonic oscillator. And what we see here is, I can actually take this L, I can actually take this L and put it down here. But what we see here is we have another second order differential equation. In fact, this is one of the simplest types of second order differential equations. It's called a homogeneous differential equation because there's a little zero over here. So again, compare the form of that equation: second derivative, no derivative, 0. Okay, compare that to what we have right here: second derivative, no derivative, and 0. Okay, same form. They're going to have a very similar solution to one another. essentially we have an electric circuit which oscillates, okay? And of course, we can see that here's the expression of the charge on the capacitor, and we notice that if we graph this, charge, okay, it's a cosine function. It's going to discharge, change its polarity, discharge. Now it's back to its original polarity, okay? And we notice that sometimes there's positive charge on the top plate, sometimes there's negative charge on the top plate. So it keeps oscillating back and forth, back and forth. And likewise, we can come up with an expression for what the current is doing, okay? The current is actually doing this, okay? I'm not sure I'm doing such a good job showing this, but you can see the current is building and decaying sort of 90 degrees out of phase with what the charge is doing, okay? Now, just like we did with the harmonic oscillator, we said that the harmonic oscillator, that omega was equal to the square root of the spring constant divided by the mass. We are going to come up with a similar relationship, but L and C were in a slightly different position. So we still have the square root there, but we see that the frequency is equal to 1 over the square root of L times C, okay? You see LC was here. In the simple harmonic oscillator equation, we had K over M. So that was a little bit different. But what this means is that the smaller the inductor and the smaller the capacitor, the faster that this thing is going to oscillate. Intuitively, does this make sense? Well, it sort of does, because if the inductor has a very small value, it's not going to store up very much energy there. So it will be very quick in terms of the time that it takes to reach a maximum value and the time it takes to reach a minimum value, okay? Same thing for the capacitor, right? If the capacitance is small, it doesn't take very much time to charge or discharge. So when we think back to our time constant for our RC circuit, right? It was the resistance times the capacitance. That the time became shorter as the time became longer as the capacitance became larger. So a shorter time would mean a higher frequency. It would take less time to oscillate. Same thing was true for the LC circuit, okay? I'm sorry, not the LC circuit. We're doing the LC circuit. The RL circuit. Smaller inductance meant less time for the magnetic field to build up. So again, this is a very, very important circuit because it provides us with a means of creating an oscillator. Something that is going to oscillate back and forth at a very regular time period, which is related to the inductance and the capacitance. And again, here we can see as it oscillates, we start with the capacitor fully charged. So Q is going to be a maximum, but there's going to be no current. The current starts flowing as the capacitor empties its charge, and current will be maximum when the charge goes to 0. Then the current is going to drop to 0 as all the charge is built up on one plate. And then finally, we go back to our maximum current and zero charge. What's interesting here is we can see that the current becomes out of phase with what the voltage and the charge is. And that'll be very, very important when we talk about AC circuits. So again, an LC circuit is the analogous, the analog of a simple harmonic oscillator. And the resonance of this LC circuit depends on the inductance and the capacitance. And again, we can, sort of match the potential energy in a simple harmonic oscillator to the electric field building up between the two plates, and the movement of the harmonic oscillator to the movement of current and the generation of a magnetic field in the inductor. Now, instead of using angular frequency, we can actually replace angular frequency with linear frequency, okay? So for instance, if I were to create a radio with an LC circuit and I wanted to tune to a very particular frequency, I would say the frequency is 1 over 2 pi times the square root of LC. If I take 1 over 2 pi, I see that that's actually equal to 0.159, and that's how I get this expression right here. But again, this is very, very simple. Just to give you an overly simple example, let's add an inductor of 1 Henry and a capacitance of 1 farad. 1 times 1 is 1, the square root of 1 is also 1. That circuit would have a frequency of 0.159 hertz. Well, that'd be really, really slow. Let's do something a little more realistic. Let me put instead a inductance of 0.1 Henry, a capacitance of 0.1 farads. That's still a very large inductance, a very large capacitance. 0.1 times 0.1 is equal to 0.01. I take the square root of 0.01, I get 0.1, and that would give me 1.59. I'm dividing by 0.1, okay? When I take the square root of that, and that would give me 1.59 hertz, okay? So what we see is that we again can use this as an oscillator, and it is used for an oscillator for a number of different applications.